Hello, ladies and gentlemen. I am going to talk today about, well, not really talk, but solve some problems from the end of Chapter 2 since we're finished with Chapter 2 as far as I'm concerned. The last two sections of Chapter 2 we do not cover. So I'm going to do some exercises from the exercises section starting on page 50. So here we go. So I'm going to start with one of the simpler problems, page 51, problem number 9, and let me pull it up. Okay, so problem number 9 says a retail establishment accepts either American Express or the Visa credit card. A total of 20.4% of its customers carry an American Express card, 61% carry a Visa card, and 11% carry both. What percentage of its customers carry a credit card that the establishment will accept? So here we go. Let's try to solve this. Okay, so let E be the event of accepting American Express, which I'm going to denote by Amex, and let's let F be the event accepts Visa. So then what is the probability of E? It's given to us as, I'm sorry, not Visa, but Amex. What is the probability of Amex? Well, 24% of the customers carry an American Express card, so we can think of that probability as the probability of a random person having an American Express card is 0.24. And we're going to convert that to percentages at the end of the problem. So 24% corresponds to a probability, if you randomly select a person, that there'll be a probability of 0.24 that they will carry an American Express card. Similarly, the probability of F, which is accepting Visa, is given by 0.61. And the probability of E intersect F, which means both cards, is 0.11. So then we can use the formula, probability of E or F, which means a random customer carries either card, is the probability of E plus the probability of F minus the probability of E intersect F, which is given by 0.24 plus 0.61 minus 0.11, and that's equal to 0.74, so that's the probability. So in terms of percentage of all customers, it should be 74%. So that should be the answer to this problem number 9. And I'm going to save this whiteboard and move on to the next problem. Okay, so in the second problem, 2 cards are randomly selected from an ordinary deck of playing cards, 52 cards, standard deck. What is the probability they form a blackjack? So I have to remind you what a blackjack is. So in a deck we have cards of value. There's an ace, which I'll denote by A, and that has value 11. And then there are cards 2, 3, all the way up to 10. They have numerical face value. So a 3 has the value of 3, so face value. And then lastly, we have Jack, Queen, King, and these have value of 10. So a blackjack is given by 21, making 21. And there's only a couple ways to do it. You have to have an ace in your hand and either a 10, a jack, a queen, or a king. That's the only way you can make a blackjack is to have those 2 cards, 2 kinds of cards, an ace and one of the 4 cards, a 10, jack, queen, king. Okay, so now let's E be the event, the number of ways to obtain a blackjack on drawing two cards. So how can we understand this? We can do this there are two ways to think about this. I'm going to think about this as drawing the cards one after the other. The probability of getting them drawn that way is you can think about the first card and the second card. And that's more convenient from the point of view of our psychology. So here's the so let's figure this out. Okay, so how many? Let's suppose there are only two ways to make a blackjack if we draw a first card and a second card. So let's sort of look at the first card. The first card can be an ace, and then the second card would be a 10, jack, queen, or king. And or vice versa, the first card could be a 10, jack, queen, or king, and the second card could be it could be an ace. Now, what is the probability of drawing an ace? Well, first of all, let's figure out the number of ways to draw an ace. Let's not actually figure out the probability of drawing an ace. I want to compute the number of ways to obtain a blackjack. So what I should be saying is that E is the event, the ways to obtain a blackjack. And the size of E, the cardinality of E, is the number of ways. So to obtain a blackjack. Okay, so now let's figure this out. So how many ways can we get a blackjack? Well, if we go with the first method of drawing a first card and a second card, so the first card would be an ace, and there are only 4 aces in the deck. And then the second card has to be a 10, a jack, a queen, or a king. Well, there are 4 10s, 4 jacks, 4 queens, and 4 kings. So how many possible cards can we draw as a second card? 4 plus 4 plus 4 plus 4, 16 possible choices of card. That's in the first scenario. And now in the second scenario, it's just the reverse order. It's going to be 16 times 4, right? In other words, it's 2 times 4 times 16. So that's the size of E. Now, what are the number of, what's the probability of E? Well, it's this numerator, 2 times 4 times 16, over the number of ways of selecting a first card, then a second card. Well, your first card is 1 out of 52 cards, and your second card is 1 out of 51 cards. So that's one way to solve this problem. There's another way to solve this problem, which I'll briefly go into. We can think about not selecting a first card, then a second card. We can think about in terms of combinations. We have 4 choose 1 ways, and then 16 choose 1. That would be the number of ways of selecting hands which have an ace in them and which have either a 10, jack, queen, or king as the other card. And then the denominator would be 52. Oops, I need some more space. Let me make more space here. I'll do the calculation here. We could take 4 choose 1. Those are hands with an ace, and then and 16 choose 1 divided by 52 choose 2. So this is the way of being dealt blackjack. This is the way of selecting a first card, then a second card. You get the same answer. It doesn't matter. Okay, so that's the answer to this problem. About 11% of the time on drawing two cards, you will the probability is of getting a blackjack. So that's the answer to the problem. Let me move on to the next problem. I'm going to save the whiteboard. Okay, so in problem number 20, this is on page 52. Suppose you're playing blackjack against a dealer. So two people playing the game, you against the dealer. In a freshly shuffled deck, what is the probability that neither you nor the dealer is dealt the blackjack? So I'm going to solve this problem now. So let's consider the following. Let's let A be the event that you're dealt a blackjack. So let me use shorthand notation for blackjack. This BJ means blackjack, and let B be the event that the dealer is dealt a blackjack. Okay, so now what do we want? Well, A union B is the event either of you is dealt, either you or the dealer is dealt a blackjack. So what is A union B complement? That means that neither is dealt a blackjack. So what we want to compute is we want the probability of A union B complement, which is the probability 1 minus the probability of A union B. So it's enough to calculate the probability of A union B in all of this. So that's what I'm going to do. So what is the probability of A union B? That's the probability of A plus the probability of B minus the probability of the intersection. Okay, so now we already computed the probability of being dealt a blackjack in the previous calculation. We know the probability of A is 0.1102, which is the same as the probability of B. So that's simple enough, that part of it. We just need to compute, therefore, the probability of the intersection. Okay, so we're going to do that. That's my next plan. Okay, so how do we do that? So let me look at there are 4 scenarios. If we consider being dealt cards in order, first card, second card, there are 4 scenarios. So scenario 1 is that I get dealt a first card ace and second card a card of numerical value 10, so a 10, jack, queen, king. And then the dealer, that's me, and the dealer has the same situation. His first card, her first card is an ace, and second card is 10, jack, queen, king. Another possibility is that my first card is not an ace, but one of the cards of numerical value 10, jack, queen, or king. And my second card is an ace, and the dealer gets draws first an ace, and then the dealer's second card is a 10, jack, queen, or king. Or the dealer's first card could be a 10, jack, queen, or king, and the second card an ace. And lastly, we can both, so there are 4 ways. Either my first card and the dealer's first card is both an ace, or my first card is not an ace, and the dealer's first card is an ace, or my first card is not an ace and the dealer's first card is not an ace, or I missed something out, maybe the dealer's, well, whatever. There are 4 possibilities. I'm just getting confused. Okay, so each one of these scenarios has the same probability, and each scenario, there are 4 different scenarios that both get a blackjack. Each scenario has a probability we can calculate. And what is that probability? Well, let's figure it out. Let's see. So it's let's talk about the first scenario. Every scenario has the same probability. To get the first card to be an ace, there are 4 possible choices for that ace. Uh, and then what? Then I have to, my second card is one of 16 cards. Okay. But now I've been dealt an ace, let's say, in my first card, and my second card is either a 10, jack, queen, or king. Now, for the dealer to get an ace in her first card, as her first card, she only has 3 choices left over because I've used up one of her choices. And her second card is one of 15 because I've taken up one of those cards of numerical value 10. So the probability of getting, that's the numerator of that scenario. And then what is the denominator of that scenario? Well, there are 4 cards drawn, 52 times 51 times 50 times 49. Now that's for a single scenario. That is, I've just calculated for the first card, I'm getting an ace in my first card, and the dealer is also getting an ace in my first card. Well, every other scenario has the same exact probability. So the answer is that the probability of A intersect B is 4 times what we just got, because there are 4 different scenarios. Okay, right. Okay, so now what we have to do is plug this in to this formula, this formula here. That's what we're going to do now. Okay, so let's do it. And so the probability of A union B is equal to 0.1102. That's the probability of that's the probability of A plus 0.1102 minus this number we just got here, minus 4 times 16 times 3 times 15 over 52 times 51 times 50 times 49. Okay, so if you calculated this correctly, we see that the probability of A union B is given by 0.9017. I'm sorry, that's not the probability of A union B. That's the answer to the problem, in fact. So let me erase that. And the probability of A union B is 0.0983. Therefore, the probability of A union B complement is 1 minus that number, which is 0.9017. So this was a harder problem than we've solved before. 0.9017 is the answer. Okay, I'm going to save the screen, and we'll move on to our next problem. Okay. Okay, so this problem is number 28 in the text, and it's on page 52. It says an urn contains 5 red, 6 blue, and 8 green balls. If a set of 3 balls is randomly selected, what is the probability that each of the balls will A, be of the same color, B, of different colors? Repeat under the assumption that whenever a ball is selected, its color is noted and then it is replaced in the urn before the next selection. This is known as sampling with replacement. The first scenario, part A, is sampling without replacement. This is an important concept in probability theory and in counting. Okay, so let us do the problem. Okay, I actually have to erase the screen, unfortunately, so 1 second. Okay, so how does this work? Well, so there are 5 red, which I'll denote by R, 6 blue, which I'll denote by B, and 8 G for green balls, right? And 3 are selected. And in scenario A, we're doing it without replacement. We're drawing without replacement, one at a time. Okay, so, and we want to calculate the probability of the being the same color, all of the same color. Well, how many ways, the event is drawing everything of the same color, how many ways are there to do that? Well, we could draw all red balls, right? That's one way to do it. So that would be 5, choose 3. 3 out of the 5 red balls, we have to choose 3 of them. Or, and that's going to give us a plus, we can draw 3 blue balls. That would be 6, choose 3 choices. Or we can choose 3 balls from the green. Now, how many ways are there to choose 3 balls from all the balls? Well, how many balls are there total? 5 plus 6 plus 8, 19 balls total. So we have 19 choose 3 choices of all selections of 3 balls. So this is going to be the probability of drawing balls of all the same color, drawing without replacement. In part B, we're going to do it with replacement. Oh, that's not true. Part B is different colors. So probability of different colors. Okay, so in the case part B, we want to calculate the probability of drawing all different balls. Well, how many ways are there to draw all different balls? Well, that's going to be the numerator of our expression. Well, we have to choose, if all the balls are different, we have to have 1 red, 1 blue, and 1 green ball. So it's 5, choose 1, 6 times 6, choose 1, times 8, choose 1, and that's divided by 19, choose 3. So that's doing this without replacement again, but getting all different balls. Okay, but what about with replacement? That's the second part of the problem. So let me save this again, and I'll do it with replacement. Okay, so with sampling with replacement, the answer is going to look quite different. So part A, the probability of same, all balls being the same, looks like this. So how many choices are there? Well, if we want to get all the same ball, well, we have on our first draw, we draw a ball. It could either be red. Okay, so that would give us 5 choices. But then we put the ball back in, and then we draw again. We want to get red again. That's also 5 choices of ball. And then on the third draw, we would have to get red again. So it's 5 times 5 times 5 if we want all red balls, 5 cubes. Similarly, if we wanted to get all blue balls, that would be 6 cubed. And if we wanted to get all green balls, that would be 8 cubed. And then what is the denominator? Well, how many ways are there drawing balls when you are supposed to replace them? Well, the first choice is, remember, there are 19 balls, so there are 19 on the first draw, 19 on the second draw, 19 on the third draw, so it's 19 cubed. So that's the probability of getting all the same if we draw with replacement. What about the probability of different in this case? Well, that's a little different. Okay, so how does that work? Well, there are 6 scenarios, right? The first ball could be red, second could be blue, third could be green, or the first ball could be blue, the second can be red, third can be green, or the first ball could be green, second ball can be blue, red. How many? So there's 6 things, right? So the 6 possibilities. Now, each probability, the probability of each one of these terms is the same as every other. So we just have to calculate this probability and then multiply it by 6. So what is the probability of first drawing a red, then a blue, then a green after we do replacements? Well, what is the so what are we doing? Well, what's the number of ways of first selecting a red ball? Well, there are 5 ways of selecting a red ball on the first draw. Okay. And then on the second draw, there are 6 ways to select the blue ball. And on the third draw, we have 8 choices of selecting a green ball. And then the denominator here is going to be 19 cubed again. So therefore, the probability of different is just 6 there, because there are 6 terms here. 6 times 5 times 6 times 8 over 19 cubed. So that's the answer to this part of the problem. And I'm going to do one more problem today. It's going to be problem number 29 on the same page. Okay, so this is problem number 29. It goes like this. An urn contains n white and m black balls, where n and m are positive integers. If 2 balls are randomly withdrawn, what is the probability that they are the same color? If a ball is randomly withdrawn and replaced before the second one is drawn, what is the probability that the withdrawn balls are the same color? And I don't know where this 90 of 848 comes from. I'll probably get rid of that. And then C, show the probability in part B is always larger than the one in part A. Okay, so I fixed the typo that was there. Okay, so let me get started with this. So I'm going to do part A and then part B, then part C. So I'm going to erase parts B and C and then put them in when I need them. Okay, so let me get started. Okay, so we want to compute the probability that they're the same color, right? So how do we do that? It's very similar to the last problem. So the probability of being the same color. Well, how many choices are there for choosing balls of the same color? Well, how many ways are there to choose balls of the same color? You could either choose 2 white balls or 2 black balls, and we're drawing balls one at a time. So the first ball we have n choices, and in the second ball we have n minus 1 choices for the second ball. Likewise, if we choosing black balls only, it would be m times m minus 1. Oops, that looks bad. Let me fix it. And it's either we're choosing all white or all black. So we're going to add, that's the number of ways total of choosing all white balls or all black balls. Now, how many ways are there to choose 2 balls, though? How many balls are there? Well, we have n white and m black balls. So how many balls total? N plus m balls total. So if I choose a ball, the first choice is, yeah, there are some dogs in the background. Sorry about that. Anyway, so how many ways of choosing balls are there? Well, in the first draw, we have n plus m choices, and we pull the ball out, so there are only n plus m minus 1 choices left over. Okay, so now let's do, the second problem was the second question was so the first part was without replacement, I believe. And the second part is with replacement. Same question. So in this case, the probability of drawing two same balls goes like this. So if we're replacing the ball, the first draw, the first ball, you have n choices. If you're going to choose a white ball, and if you're going to choose a white ball on the second try, well, you have n choices again, so that's n squared. Similarly, if you're going to choose two black balls and you're replacing them, it's going to be m squared. And then how many choices are there? Well, it's now n plus m squared choices total for drawing anything. Okay, so now in part C, we want to show that the probability that you get in part B is bigger than the probability that you get in part A. So we want to show that n squared plus m squared, so we have to show this, over n plus m quantity squared is strictly greater than n times n minus 1 plus m times m minus 1 over n plus m times n plus m minus 1. So this is going to lead to some algebra that we have to do. So let's do the algebra. Okay, so I've moved the inequality to the top of the whiteboard, the new whiteboard, because we're going to have to do some manipulation. So I'm going to multiply both sides by a single factor of n plus m in the denominator. So that's going to lead to n squared plus m squared. So this is what we want to show. So I'm going to put a question mark. Is this a true statement? So we get n squared plus m squared over n plus m. Is that going to be greater than or equal to n times n minus 1 plus m times m minus 1 over, well, we get rid of one of these factors here. It's n plus m minus 1. Now, every number in sight, numerator, denominator, is a non-negative number, so we can cross multiply here. So this is equivalent to asking, is n squared plus m squared times n plus m minus 1 bigger than or equal to n times n minus 1 plus m times m minus 1 quantity n plus m. So I've done the cross multiplication. Okay, so that's the question. Now I can rewrite this, the right-hand side, as in the following way. This is, by expanding, this is n squared plus m squared, and then we have to subtract off n and subtract off m. That's what you get in the parentheses on the right side. Let me clean this up a bit. And then multiply by n plus m. Okay, so that's what we get so far. And so on the other hand, so this is the question. If you look at the left side, we could sort of distribute, and the left side becomes n squared plus m squared times n plus m minus, from this 1, n squared plus m squared subtracted off. And so we're asking whether this is greater than or equal to the stuff on the right side, which I could also write as n squared plus m squared times n plus m, but we're subtracting off n plus m quantity squared, right? That's because that's from this term here that appears multiplied by n plus m. Okay, so now we can get rid of both of these things, cross them out, and then we can multiply by minus 1, changing the inequality. So then you're asking whether this is true, or actually even better, yeah, right? You're asking whether or not, this is equivalent to asking whether or not n plus m squared is greater than or equal to n squared plus m squared. But the right side is n squared plus 2nm plus m squared by the binomial formula. And this 2nm is larger than 0, so this checks out. This works, and that does it. So this was a bit of work, but not impossible to do. So I think that's enough for this lecture. Okay.